Welcome to TAF 2023. Today's session will be Enterprise Scale Data Science Lifecycle. My name is Vev Gadagiri, and I am a lead data scientist for the Spotfire data science team.
Hello, thank you for joining this session. My name is Julieta Diaz, and I'm a senior data scientist on the data science team. Hugo, do you want to introduce yourself?
Hi guys, my name is Hugo Peters. I'm a product manager for the developer experience at TIBCO.
Cool. So here's our disclaimer slide. As a reminder, the following information and presentation belongs to Spotfire software. So we're going to get into the agenda. We're going to talk a little bit about the Spotfire stack before going into two demos, one in the field of high-tech manufacturing and another in the field of insurance, where we'll represent the Spotfire stack before we'll look at some takeaways and finally leave the users with some references to go back to. So let's dive right in, right? So we're going to talk about the data science and analytic process at Spotfire. So we start with the project definition. We go into data acquisition, blending, and exploration. Often during this phase, we do rescope depending on what data is available. So we would again go through the process of blending the data again. And finally, we generate features that would be used downstream for our machine learning algorithms before deciding a baseline model. Once we have a machine learning model in place, we look to further refine this model and further test this model before deploying it and monitoring it in production. So the process that I just went over, we'll try to assign where the Spotfire tools fit in and some of the personas that also come into this. So as you can see on the screen, there is the Spotfire that kind of sits in the center of this. And the Spotfire in itself is talking to typical data virtualization or TDV, Spotfire data science, Spotfire streaming, and model ops. So the business analyst is the persona that directly interacts with the Spotfire application through parameters, which would then invoke jobs in Spotfire data science and typical data virtualization, where the data scientists and the data engineers are contributing to. And then you have the final model that gets pushed into our model ops platform, where the machine learning engineers can deploy this in production and further visualize that in Spotfire itself. So I'm going to wrap this up with the solution summary of what we just saw. And I'm going to focus on three main things here. And we really looked at this from the standpoint of making this more explainable, the platform as a whole. So the collaborative, no low-code platform, which is a Spotfire typical data science platform. And then it is also an end-to-end data science platform. So it does lower the cost for data science projects and makes the models more trusted. They access data from anywhere, as we just saw the tight integration with typical data virtualization, which provides us access to more than 350 plus data source adapters. You could also directly read the file and write the file from Spark, and then, or you could just write it back to the data source in itself. So this also reduces a lot of the data cost, and the optimized models can then be trained on all the required data that would be accessed from TDV. Finally, the extendable nature of the platform, which allows multiple personas to work on a project at the same time, from using Jupyter notebooks to easily integrating code base into point and click and drag and drop operators. Okay, so now I'm going to get into the first of the two demos, where I'll be talking about how we can optimize yield in a high-tech manufacturing process. So this process in itself consists of 5 stages, which goes from masking to etching to wire bonding to a final test phase. And these stages in the process are sequential in nature. So what we're going to do is we're going to monitor the yield and detect anomalies in the process that influence the changes in this yield parameter. So I'm going to start with typical data science, where we're going to go over the steps involved. We'll begin with pre-processing of the data, which involves blending of the data from multiple sources. We'll then explore the transform data in Spotfire and then go back into Spotfire data science to generate what we call as the root cause analysis table. And based on that very table, we'll train a few machine learning models that will predict yield. And then we'll hop back into Spotfire one final time to perform explainability of the selected model. So you can see we're doing quite a bit of hopping here, but it also speaks to the fact that these tools are very tightly integrated, and you could use each of these tools for their own strengths. So this is the typical data science workspace, and I'm going to go right into this. So the first step really involves looking at the statistical process control data, right? So what we're doing here is we're taking this data and we're performing some pre-processing. And the very first step of the pre-processing would involve in actually looking at the data and converting all the numeric data into a given range so that we could actually use these columns downstream to train our machine learning algorithms. So here's a very simple script that does that. It takes in the data and then outputs the range. And you can actually further push this data down to typical data virtualization, or you could also just push it back into the workflow in itself. We're also looking at the manufacturing record data, which consists of the lot information. And we're generating two new features here, one called the duration and one called the yield, looking at the pre-existing logic. And yield would be what we'd really monitor. So once we have kind of this data prep set up, we're then going to move into Spotfire, where we're going to visualize this data. So I go in here. So starting from top left, we can see that we're visualizing duration versus the lot, and this is colored by each of the stages in the process. As I said, there are 5 stages that make up the process, beginning from masking all the way till final test. On the right side, we're visualizing the yield by the lot, and each of these are trellised by the stages in the process. The dotted lines really represent the 10th percentile line for the yield. And what we're really trying to look at is, if you look at the final test phase, we're looking at lots that come below these reference lines, and these would be of interest to us. Now, just moving over to the left, we're also drilling down into one specific stage in the process, which is the etching phase, which consists of 8 parameters. We visualize these parameters over time, and they're colored by some of the machines that are assigned to them. So you could look at that. We could just go over this window. So once we've done this, we now kind of are ready to move into our step 2 of the process, which would involve building out the root cause analysis. Now, we previously visualized the individual etch parameters over time. So what we want to do here is to combine this SPC data with the final yield data that's going to come from the manufacturing data. So we want to observe the presence of any relationship between what we're looking at that point versus what we see at the end, just to make sure that, this is a sequential process and we're capturing the right metrics at the end. So what we're doing here is we take the manufacturing record data, we isolate the test phase, the etch phase, and then we join this back with the SPC data, and the final data set then is joined back with the yield from the test phase. So the final data set would look something like this, where you have the yield information by lot, and each of the etch parameters are the column values. So we're going to go back into Spotfire one more time, where we're writing that data set back into TDV, and those views are consumed in Spotfire. We're visualizing the range of values here over yield, and they're trellised by each of the etch parameters. So the range of the values in itself, we played around with the logic here, and we felt like the difference of the minimum and the maximum values gave us the most distinct patterns. So looking at the last trellis chart of RF phase error, we see a very distinct pattern, right? So when the range of the values is at around 0.7, the yield is hovering between 97 to 99. But when it's close to 1, we can see that the yield is sharply dropping off. And at this point, we do have a hypothesis that is RF phase error really contributing to the drop in yield. So to confirm this hypothesis, we go back into the typical data, the Spotfire data science platform, and then we're going to build a model that will predict yield. So we take the same root cause analysis table, We perform some transformations so that the column values now become the columns. We then sample the data, and we trained a few machine learning algorithms here. So starting from gradient boosted tree regression to elastic net linear regression and random forest regression. Looking at all the three, we saw that the random forest gave us the best results. Now, if I just sort this, and you can see how the phase error does show up on top here. Additionally, we can also look at some of the other regression evaluation metrics, namely root mean squared error, R squared, and the explained variance. So once we're done with selecting the model of our choice, we can then export this model to ModelOps, where we can further calculate drift on the model and build scoring scenarios. We can also export this model to the local workspace itself. Now, if I go back into that, you can see that I've actually written this model out into the workspace. Now, the one final stage to this is once we are done selecting the model of our choice, we then perform an explainability on top of it using the SHAP explainer, where the input to the SHAP explainer would be our random forest model file. The results of that is also written back into TDB, where it's visualized into Spotfire. So quickly looking at the explainability, on the top left side, we can see that the same table has been imported over from Spotfire data science platform. And then here we're also generating the test data predictions. So this test data predictions table consists of the lot and the results from each of the model. Now, if I sort this by the lowest value of the yield, because that's what we're interested in looking, and if I click on one of these lots, moving over to the right, you can see how the RF phase error contributed the greatest in bringing the prediction of the yield into the more negative side. And the same thing is also confirmed by moving over to the right side, where you can see that the phase error is actually on the extreme side of the spectrum. So the one other thing that we also noticed from here is that this seems to be coming from one specific machine. So if you look at the bottom graph, to confirm this hypothesis, we go back up at the top where we click on the tree map. If you click on the phase error, and yes, this does seem to be coming from one specific machine, which is PQ212. And you can see that this is associated with the lower yield, and the color just indicates the extreme values of phase error. So at this point, not only have we found out that the RF phase error was responsible, but it's also coming from a specific machine. I'd like to now hand over to Julieta, who will walk us through over the dynamic pricing in insurance.
Thank you, Wahida. So welcome to the dynamic pricing demo. The use case of this demo is the insurance market. However, the principles applied are valid across a range of business domains. What we are looking at here are the different steps that this demo will cover. So insurance brokers can optimize the pricing of policies they offer to customers by being able to predict the probability of the customer accepting an offer. And this allows for different commissions to be applied. For example, for high chance renewals, they may add more commission, or perhaps for some customers they are not interested in, they may also increase the commissions. So the data that we are looking at here represents insurance customers who have received an offer for a policy purchase. And the goal here is to predict the response variable. It's a binary column that indicates whether a customer will renew their policy or not. And the other variables represent information that could be used to predict customer purchases of an existing offer. We are interested in determining how these variables are related to offering acceptance. So here, the data set has been retrieved by a connection to data virtualization from Spotfire. We use a simple workflow in Spotfire data science to randomly downsample the data, then create a new data set in data virtualization, and then Spotfire reads the data set that we are looking at. We can also modify the downsample input box and click the button which triggers the Team Studio workflow to create a new downsample data set. So what we are looking here, it's a simple Spotfire only page where we can analyze some of the data. The top two bar plots analyze categorical data, and the bottom graphs are for continuous data and help us to compare the distributions of renewals versus non-renewals. You will notice that this demo follows very similar steps to the demo that Vahiba showed before. So this page is where we call Team Studio to build three models: elastic regression, random forest, and boosted trees. There is a suite of hyperparameters that we can also modify. And this is sent to Team Studio when we click the Build Model button. So as you can see, some of the inputs are comma-separated lists of options. This means Team Studio will generate multiple models with all possible combinations of hyperparameters. So in fact, it's doing a manual grid search to find the optimal model. We can also review the raw curve and the goodness of fit metrics and decide which model performed better. In this page, this is the evaluation page. We can explore the probabilities and understand how the model is actually classifying the two different groups and how accurate it is. The bar charts in the middle show the distribution of probabilities from each model. Below this, there is a confusion metric that allows us to compare the different categories predictions. On the top right, it's the results from the grid search of models. And then we also have the overall F measure of each model per category. So this is the final step for this tool, and it's a very simple one. You just need to select the model you want to deploy and click the button to deploy this model. This triggers the third workflow, which will export the model to model ops. So with the creation of a good model, maybe the work of the data scientist is done, but it's not the end of our use case. So we have a model, but if we don't use it, it's useless. We would like to incorporate it into business processes and decisions. This part is it's about how to apply the model to the new real-time data or batch data and provide the value of the model. So for that, we will use the Model Labs platform, which has the role of the scoring engine. So the model will be sitting there and contributing with predictions for pricing decisions. So here, the renewal best model is exactly the model which was exported from Team Studio. We can see the model was exported and published 6 times. Together with the model object, Team Studio also exported input and output schemas for the model. These are in model ops needed to define what are the expected input and output data structures for the model. So you cannot use the model as a standalone artifact. It needs to be incorporated into the scoring flow. So the first block is the scoring flow. In this scoring flow, it's an input block where you define the input state expected structure. After that, we have a Python step that in our case, it's just applying business logic around what to do with probabilities from the previous step. And finally, the output block, it's defining what will be included in the final output. So we have the scoring flow defined, but this scoring flow, it's only a limited set of steps and calculations. It's not an artifact that it's actually be doing the scoring. So for that, we are defining scoring pipelines. So the scoring pipeline is using scoring flow and so-called inputs data channel and a data sink. In our case, these data channels will be Kafka streams. So from customer systems, the data is flowing through Kafka. So if we grab the output of Kafka data sink by, for example, Spotfire streaming, we can visualize it in Spotfire. So on the dashboard here, we can see the quotes coming in real time and showing how our premiums are behaving in time, and some other relevant streaming information about regions, distributions, and breakdowns by age. So I hope you enjoyed this demo. I will now hand it over to my colleague, Hugo, who will talk about composability.
Thank you, Julieta. So last but not least, I would like to wrap it up and show how you can bring this together by composing applications. In this case, we want to compose basically the analytics that Julieta was showing you earlier and putting that as part of a workflow and creating a composable application. But this is obviously just one example of a composable application, and you can create all sorts of composable applications. In this case, we defined a workflow, and every step of the way of this workflow, the user will be presented with a Spotfire analytical report. And based on the information that he finds in that report, he can obviously make his decision. And when I'm doing the demo in a minute, I will do each and every step of this workflow, but you can obviously imagine that the various steps could be done by various people. So for example, comparing campaigns could be done by a business analyst, evaluate risks could be done by another person of the department, the explainability could be done by a data scientist, and the prepare production could eventually be done by an administrator. So let's dive into the demo. So what we see here is a map of the UK, and we see the various counties in the UK. And on every county, we basically have a data science model running to create the quotes. And we also see how these models are behaving. And we see that one county is actually behaving badly or not so good as the other ones because it's red. And we see another county where it's green. So what we want to do is we want to start this investigation to see if we can basically deploy this model from that county to that county. But we don't want to do that directly. We do want to run an investigation where we basically want to determine if the model does not become biased, so become racist or sexist or something like that. So here we go into the first step where we basically will compare the campaigns. So it will load up the analytical dashboard here. And here you see the same dashboard that Julieta was showing earlier. And here you can basically dive into the comparison of the campaigns, and you can eventually say, okay, I make a decision, the strategy is good. Then you submit that, and then you go to the next step. In this case, a business person will determine if there are certain risks in deploying this model, and if we need to evaluate these risks to see if there is outliers compared to age or sex or something like that. So what we will do is we will say further investigate bias. That will then send it to a data scientist. And then we go to the next analytical model. Their data scientist can do her or his investigation and basically see what are the, let's say, attributes that have the most influence on the model. So in this case, we will say, okay, there is no risk, and we will submit it. And then we are going to prepare the model for production. So now we will go to the next step, prepare for production. We see all these different counties, and we'll click on the button, go to production. We select the county that's doing worst, the red one, and we'll basically say submit. So we will apply that model into that county. So if we submit it, we go to the next step in production, and now we can actually see how the model is behaving in real time. What is also nice is that basically every step of the way is stored. So it's basically traced. Now, after we've run this process, we obviously hope over time that this red county now will become green again. So what I've shown you is we went through this entire model, and every step of the way we presented the user with a dashboard that gave him the right information to make that decision at that step. Now, this is obviously an example process. You can basically implement any kind of process that you want. And with that, I'll hand it over back to Vaibhav, who will wrap it up.
Thank you, Hugo. So I'm going to wrap up with some key takeaways. So Spotfire platform supports the complete data science lifecycle, including training of the model, optimizing the model, evaluating the model, and finally explaining the model. It emphasizes real-time model deployment and AI decisioning capabilities for applications like optimizing yield in manufacturing and dynamic pricing in insurance, and across many other use cases for different verticals. With the typical platform, you can create composable applications as demonstrated by Hugo, which allow you to gather insights from your data and act upon these insights in a traceable manner. So some next steps and resources, these demos and a lot more can be found on the public interactive Spotfire demo gallery. Demos that we have shown not only focus on Spotfire, but also Spotfire applications that are powered by other data science engines like Python and R and Spotfire Data Science Team Studio. Some of the additional examples are customer analytics and hospital management that we recommend you to check out. We refer to these AI apps, and there is a great introduction to Spotfire AI apps session available at TAF, which we recommend for you to watch. Thank you.